when we have the time domain source, let's call it, I am cos omega t phi, and we can just like the impedance, we write as phasor. Similarly, a voltage source we write as phasor. Similarly, any linear source can be, in terms of its phasor. If it's VT, RICT, now we just convert it to the phasor domain. Similarly, node analysis, mesh analysis, everything that you apply in DC circuits that you learned so far, the Thevenin, Norton, how you calculate the power consumption. You just do it in phasor domain. For instance, let's look at this circuit, the RL circuits. We found that, this is a VM cos omega t, and we wrote it because amplitude is Vm. There is no phase cos omega t, no phase added. So that the phasor will be this. The impedance is R plus the impedance of the inductance J omega L. So we can find the current. What's the amplitude of this?
It's 5.
The logic is take the square of this, take the square of this, and then put it into the square root. So that's what it does here. So you find the amplitude, and then to find the phase, you use the tangent inverse. The phase of this is tangent omega L over R, but because it's a denominator, you put a tangent inverse, okay? That's how you find the phase, because the phase of this is 0. So 0 minus tangents of this signal. So why is it tangent? Well, so R is here, omega L is here because it's J term. This is omega L, and this part is the R. So trying to find this phase, right? So the phase of this will be tangent inverse omega L over R. So let's say this is a 3, 4, 5. So this will be angle 37, right? So, and that is actually tangents 3 over 4. So same logic here. You know these phasors. If I ask you, hey, draw these in Cartesian domain, you should be able to do that. What is this in Cartesian domain? It's Vm, phase is 0, right? So a Vm signal, phase is 0. So what would be the voltage of this resistance, for instance? Well, we find the current already, and it has a phase of -5. Resistance has no phase, purely real, right? So current times resistance will be the voltage of the resistance, and its phase will be same, -5. So it's VR. And then the voltage drop on the inductance is, again, this current. And now, this time, it is the impedance of this inductor. And let's call it, ZL. And that is J omega L, which has a phase of 90 degree, right? So 90 minus this phase, because this has a phase of 90 degree. When we multiply them, we added the phases because they are exponential, right? This means exponential J 90. This means exponential J -5. So when we multiply them, we are basically multiplying exponentials, which means we are adding the phases. So 90 minus 5 is this phase. And in phasor domain, it's extremely nice because you can make additions and subtractions. So if you look at here, this is the R, VR. We add the voltage VL, and this is basically we are doing KVL, right? So now we are back at the voltage lecture, or you can do it like opposite. This is the voltage, we wrote the phase, we take the voltage off VR. Now you find the voltage L. So again, this is the voltage VS. You take the voltage drop on the R, you subtract the vectors. You are here. Now we found the voltage drop via the equivalent vector. We just did KVL. We added the vectors. Voltage minus voltage drop equals this. It's extremely important. And now let's do an assumption. Resistance is much bigger than J omega L. So basically your impedance Z, it has a resistance part, it has an imaginary part, right? So I'm saying resistance is much bigger than J omega L. So this one, VL, will be so small, right? Then we can say, hey, your VR will be equal to Vs because this VL is so small. Or vice versa, resistance is so small than J omega L. Now you can say, hey, my voltage drop on the resistance is so small, so VL will be equal to Vs. The voltage drop on the inductor will be mostly Vs. For instance, in RC circuits, how we can draw this? Well, the logic is same. So this one, we assume the phase is 0. So it will be Vs here. And you find the currents, and doing the complex equations, you find the phase of this current. And resistance has no phase. So multiplying it with this current, the voltage drop will be having the same phase. This is VR. But the cap has a phase of minus 90. So multiplying this current with the cap impedance, which is minus 90 degrees, as you can see, you'll be adding minus 90 to the phase. So your cap voltage will be this one, right? This minus 90. So it comes somewhere here, let's say. So 90 degrees this. So you are subtracting 90 degree from the actual phase. So this is the phase, subtract 90 degree to find VC. All right. And to summarize, like I just want to emphasize that you can do KVL, KCL, series, parallel, delta Y simplification on the resistance conversion, source transformations, Thevenin, Norton, node voltage method, mesh current methods. They are all still applicable. Same logic to the sinusoidal steady state. So instead of the time domain, we now use phasors and we also use impedances. So for instance, if we write bunch of R's here, you sum the R's, right, in series. So if you put a j omega L here, well, you'll sum them again. R plus j omega L, let's say this is the cap, it's minus j omega over j over omega C. So the same way you'll sum them. If you do the parallel, same logic, but now you'll use the term impedance. So the complex terms will come into the equation. Okay? Same logic for KVL. You sum the voltages, equate to 0. KCL, you sum the currents, it will be equal to 0. You can do the node voltage methods or mesh current methods. Okay, still. So here's an example, an inductance with the cap in series, and we find the equal impedance of the circuits. This will be the inductance impedance. This will be the capacitance impedance. So we sum them up, it's this, minus J75. Let's say they're in parallel, the same logic, you put the numbers and you find the equal impedance, okay? So there is a circuit example here. I won't go much into the details, but it just shows you that you can solve this circuit now using the impedances. You write the impedance of, you already know the resistances. You write the impedance for the cap and inductors, and then what's the equivalent impedance? It's Z1 plus Z3 in parallel with Z2 plus Z4, right? And you put the numbers into the equation. You write these things in terms of polar coordinate, and your job becomes much easier, and you find the equal impedance, okay, of the circuit. And now you can simply write this circuit, with a voltage source and equal impedance. This shows the phasor diagram, for instance. Just because you found the impedances, for instance, if I ask you what is the current here, well, that's the voltage divided by equal impedance. You see here, right? Well, you found the impedance in the previous slide, then dividing voltage by that impedance gives you the current, right? IS. Well, now you found the IS, you want to find the IC. Well, you just do the current division. There is this thing called current divider, right? So if you want to find the IC, you find this current, you multiply this IS with this impedance, and then you divide it by the total impedance. Well, that's called current division. It's not like just specific to the phasors. There's current division, there's voltage division, right? So the formula for the current division is, let's say you have current of 5 amperes here. So let's say the resistance is here 4, and let's say the resistance here is 1. Okay? So the current here will be this total current times this resistance divided by total resistance, like not the total, like it's sum of the resistance. So 5 times Z1, I'm just writing in terms of impedance, divided by Z1 plus Z2. So that's what it's doing here in the current division, right? So for phasors, the logic doesn't change, as we mentioned. You apply the same technique, okay? And here it shows all these things in the polar coordinate, okay? And you can see that, for instance, the total current IS is sum of IC and IL. IC is here. You sum it with the IL vector, you come to the IS vector, right? So let's look at the power consumption in phasors. In time domain, you know that power consumption is voltage times current. And you multiply the amplitudes, you multiply the cosines, and then you get this signal. And to calculate the average power, you integrate it in a period, and then you divide by the period. That's how you find the average power, right? So the first term in equation 1, here this term goes to, it has an average value of 0. So this doesn't really contribute anything. And so the equivalent power is basically in time domain is that 1/2 VMIM times a constant, because this is sinusoidal. When you find the average power absorbed, right, if you take the integral of a sinusoidal, this will be 0, right? It's in omega t. Why it will be 0? Well, integral means you look at the area. Area is positive here and area is negative here, so this becomes 0. So the power for the first term is 0. For the second term, because this is a constant, cos angle minus another angle, this is where your power comes from for a sinusoidal signal. Okay? So knowing this and applying it to the phasors, so we know that in time domain this is the power for the any impedance, so this impedance can be resistance, this impedance can be inductor, this can be capacitor, or it can be combinations of these in series and parallel. And now for the resistance, you know that, let's assume current has an amplitude and a phase. Well, we know that voltage will have the same phase times that resistance. So putting those things into the equation, we know this is Vm, so we write the Vm here. This Im write it Im here, and we write the phases. The phases are same, so this becomes cos 0, right? So cos 0 is 1, so you basically got the famous power equation. The power is 1/2 current square times resistance, or 1/2 voltage square over resistance. So the phases doesn't have to be same. As we mentioned in the inductance, the voltage phase is leading, and in the cap, the voltage phase is lagging. So when we write these equations due to these phasors, we can simply write the power, and you can see that the actual average power will go to the 0 for the inductance and the capacitance. Okay, because here we have the cos 0, and here we have cos 90 degrees, and we have here cos minus 90 degrees, which becomes equals to 0, so that we can say for average power for an inductor or the cap goes to 0. Okay. There is also the maximum power transfer you learn in this class. Let's assume these are R. Let's say this is the Thevenin resistance. You found the complicated circuits. Well, this load resistance should be equal to the Thevenin resistance for maximum power transfer. But this doesn't have to be resistance. This might be inductive or capacitive, right? And when you look at all these equations and stuff, now we have different phases. What we find is actually the load impedance should be the conjugate of Thevenin impedance. Okay. Now we are talking about impedance, not resistances. And that's actually what the real life is. Nothing is really purely resistive. It is a JX, a reactance part due to the inductance or cap. So for maximum power transfer, this one now should be the conjugate of this. ZL should be conjugate of ZTH. And conjugate means you take the imaginary parts and you make it minus. So here you just put 180 degree to the imaginary part. So now the conjugate of this is R minus JX. Okay. So like simple example, we have a source and we have an op-amp, like in a feedback, and we have a load here, and it's asking what is this load impedance should be for maximum power transfer to the load. Well, you find the impedance of this op-amp output impedance. It will be, let's say, 50 minus 30J. Okay, because you find this output impedance, you can simply write this Thevenin. It will be a voltage source and this output impedance, RTH, right? Or ZTH. So it is 50 minus 30J. So can somebody tell me what should be this impedance for maximum power transfer?
50 artı 30J.
Super. It should be the conjugate of this. You can look at how we derive these equations. I won't go through, but it is the same logic, with the maximum power transfer in the real part, the real domain that you learned. Now it's just, as you can see, imaginary parts come. And because the denominator must be small, basically this imaginary part should go to 0. That's why the imaginaries should be conjugate of each other. This must be 0. So whatever you see minus J conjugate becomes plus J. Okay. But the real parts, as you see, 50 still stays. So let's go to the next one. There's an example here. There's a voltage source. There are a bunch of impedances. Asks you what should be ZL, right? So what you do is you find the Thevenin of the circuits, and then the ZL becomes just the conjugate of that Thevenin. There are some questions here, that you can use of the phasors, a series RLC circuit, just like a first order circuit, it can be a second order circuit as well, So you can apply Thevenin, as I mentioned, same logic applies. So you have to do, for instance, two nodal analysis. If you look at the circuit, let's solve this Thevenin quick. So for instance, this diagram is given to you, the circuits. So this is cap, impedance of minus 40J, voltage controlled voltage source, impedance here, resistance here. So here, for instance, you can just do a simple source transformation here, right? 120 divided by 12, you do a current source with a resistance. Then these resistances are in parallel. You find the equivalent resistance with the current source, and you can again convert it to the voltage with a series resistance, if you like. Just, you can do it. You don't have to do it. You can just do the nodal analysis quickly. So then after doing that, you write a KVL here over this loop. And after doing that, there is this Vx in the KVL. You can write the Vx 100 volts because phase is 0 minus 10I. But don't forget, these are phasors, okay? So, and then putting this Vx into here, this equation, you solve the circuit V and I. As you can see, you found the I, then you can find the V, and it's asking you what is the V Thevenin. So simply knowing the I and the V, the Thevenin, you can find the Thevenin